Okay, guys, I've heard a lot of complaints about LRP carburetors, why they have tuning issues. So I had one extra, so I decided to compare it with an HPI RTR carb that I had lying around. So I took them apart and made some illustrations on differences. Here on the left you see the parts and how they arrange on the carb for the HPI on the left and the LRP on the right. They have the same amount of parts, but the designs are different. I've also sketched on the bottom here the internal volume or geometry of the carburetor body. So to start, major thing I saw off the bat, kind of already know this, is the HPI is a composite carb. What does that mean? It has two different materials. It has metal on the sides. It's through the plastic body. I think the plastic body is molded onto it, so it's metal all the way through, but it has the composite or plastic or nylon body molded over the metal. It's actually aluminum. I checked it, it's non-magnetic. I have the boot and the piston. This is kind of what opens up the carburetor's percent of airflow. On the HPI, it is magnetic. Then we have the low speed needle. It's non-magnetic on the HPI. It's brass. It has two O-rings on there, and the needle is on the front. That shuts off the fuel coming in from the high flow jet or the high speed needle. If you look down in there, you see the hole, the orifice that needle throttles the fuel across. So as I say, it has two O-rings, and the threaded portion is up front. Now it goes and threads right into the nose of the piston. That's a good design because it controls the alignment closer to the needle, so you don't get like a misalignment when the needle or the piston slides. And it also has two O-rings to provide a good seal. This is very robust for air ingestion. Now let's talk about the volume inside. So here on the top I measured the entrance open area to the top here, and it's actually around 12.2 millimeter, and then the throat, or where the venturi is, it's 7.5. So on the spec sheet, when you see an open area or an open diameter of carburetor, this is the number they advertise, the throat diameter. Now on the exit here, it opens up to 9.7. Now the venturi, what it does is it creates a pressure differential across the throat to actually pull a vacuum or a lower pressure in the throat here, and it kind of help pulls the fuel in. So the bigger the diameter between the throat and the exit, it's a more powerful pump as per se. But there is a point of diminishing return where if these whole diameters are not tuned right, it will not work. But around 2.5 millimeter of diametral difference seems to be optimum. So you could tell you would have a bigger diameter here, so you kind of have a higher pressure, and then you have some losses because you're choking off the flow, so you create a lower pressure here that pulls in the fuel from the high-speed needle and sends it to the inlet of the crank. Now, this design seems like it's optimized for a faster pull, so it will have a stronger suction or flow rate inside that crankshaft. Mind you, this is from a smaller engine. It's from the 3.5 HPI RTR F3.5 engine. Now, did the same comparison on the LRP. It's for a bigger engine, 5.4. Comparing the low speed needle, it only has one O-ring. It's guided by the threads way in the back here, and then a long cantilevered needle that protrudes all the way into the body. That has that opening from the high-speed needle. I place the needle in here, and it doesn't really seat. It pushes all the way down, as opposed to the HPI. It stops right at 3/4 right here, so it does shut off or seat in the body at a better way than the LRP. It seems like the LRP will always have some flow, and the flow area of that needle is large. So you could tell it has a more of an exponential as it opens, as opposed to kind of a more of a linear with this design. So you could see off the bat that this design will shunt more fuel for a given travel. So the piston here is aluminum, non-magnetic. It seems like it's anodized coated for wear resistance. The body is also aluminum. Sorry about that. So one of the things I realized is with this being aluminum and the body being aluminum, you could see that it's very susceptible to thermal growth and also contraction during cooling. So it's not ideal from a flow perspective, where if you start the engine cold, it will have a different clearance, as opposed to when it heats up, it opens up more. So it affects your tuning. One of the things that LRP did on this design was to add this, I don't know if it's ceramic or hard plastic, to kind of isolate some of the heat from the engine. But personally, I don't think that's very effective. Because the body itself is all aluminum, as opposed to the HPI design. It's shielded entirely from the engine and the atmosphere as well. So if the environment or ambient temperature is hot, it doesn't affect this, so it's more stable, as opposed to the LRP. It's all aluminum, so the outside exposed area of the carburetor body will soak up the heat from the environment. So all of the parts, internal parts of this design is magnetic except the needle. Now again, this is bad because the entire aluminum body will grow, and the needle, it means steel, will grow also, but aluminum is 3 to 4 times the expansion rate of steel. With this design, as I said, it's non-magnetic, it's not aluminum, it's brass. Its expansion rate is close to aluminum. So that's one of the reasons why they make the piston and sleeve of the natural engine of brass and aluminum pistons. It maintains a good clearance when temperature is hot. So I think this is one of the main reasons why the HPI is more stable, or traditional or other carburetors are more stable than the LRP, mainly because of design and materials they selected. Now let's talk a little bit about the flow, the areas in the diameters in the LRP body, because it has the option of putting in various venturi sizes. This is a 9mm venturi. Now a 9mm means the open area of the exit here. So inside the carburetor, there's pre-drilled straight hole right there with a step, and this is pressed all the way in. This is pressed all the way in here, and then this diameter here is 9mm here and here. It matches with the exit diameter of the venturi. Now that being said, if you put a venturi in here that's say 6.5 or say this one is 7.5, you see the throat, you can see the throat area is smaller, the exit diameter is smaller, and it breaks into a 9 here. So 7.5, for example, I'm showing you 7.5 here, 9 here always, because that's what I measured down in here. The exit is 9, and 10mm always on the exit. So you could see that having these different inserts will give you various, performance, because you are changing only the inlet size through it here, and nothing else is allowed to change, as opposed to the HPI design where you can't change anything. It is what it is. It's optimized. If you were gonna like open this up to say 8.5mm, you would want to open this up to 8.5 as well. I measured this diameter and this, and they're all and it's the same. You want to keep these two the same, and you could play with these N1s and open those up. But overall, it's looking like, the HPI design is better than the LRP. Your delta P, based on the change in diameter here, I don't think it's a lot. It's 1mm of difference, and I don't see that having a stronger suction than this guy here with the 2.2 millimeter diameter difference of diameter. Okay, I think that's all I have. Again, LRP on the right and HPI on the left, comparing both carburetors, design and geometry, to see if we could figure out why the LRP does not have a good tuning ability versus the HPI.